So when I made my talk, actually, I was kind of wondering what title I should give it. So here I choose like a very serious title. It's called "From Bell Inequality Violations to Device-Independent Two-Party Cryptography." But for a while I was also wondering whether I should call the title "Proof by Experiment," or possibly whether I should go for a more fun title like "Testing Nature for Fun and Profit." So the kind of big theme actually that will, I guess, shape my talk. In fact, all of what I'm going to talk about is about just one single idea, namely this one. So we know that kind of we might observe a violation of a Bell inequality, and I guess we'll have to think about what this means exactly. And we want to know, can it be that we violate a Bell inequality and at the same time a particular statement holds? I guess the big theme of this talk will be to show that they cannot be true at the same time. So we're going to plug in all kinds of different statements in the statement box. And our kind of overall goal will be to conclude that kind of if we violate the Bell inequality violation, and that is of course something that one can observe in an experiment, one can test this, then we can conclude that the statement we want to establish is necessarily false. Okay. So of course, this is an experiment, so we also have to think about what it exactly means to observe a Bell violation. But the kind of beautiful thing is that kind of Bell inequalities do allow us to establish, so to say, statements, or rather the falsehood of certain statements, or gain confidence on them, to be precise, by doing some experiment. Great. So this is basically what this talk is going to be about, and how we're going to exactly do that is in a few steps. So I will first talk about testing properties of nature, so meaning that the statement that we're going to put inside this box is actually a statement about nature. And I will talk briefly about the loophole-free Bell experiment which we've done in Delft. And I will spend a roughly equal amount of time talking about what actually a Bell test establishes, and also what it does not establish. And I guess in the second part I will then, let me call this use, go to the fast of using nature. So we'll talk about device-independent crypto, in particular outside quantum key distribution that you may be already familiar with. And here kind of the statement that we'll plug in, so kind of security does not hold, and we'll kind of show the falsehood of this. Okay. So the first part of my talk is that we replace statement by, say, the experiment can be described by a locally hidden variable model. And I guess most of you know that kind of the violation of a Bell inequality is inconsistent with the fact that the experiment can be described by a locally hidden variable model. So they cannot be both true at the same time, meaning if we observe a violation of the Bell inequality, then we know that the experiment cannot be described by a locally hidden variable model. So, like I said, I want to talk a little bit about this experiment in Delft, which was done by quite a lot of people in Delft, chiefly my experimental colleague Hanson and his group, and also David Elkouss, who's in my group, and actually quite a lot of other people. So I guess for most of you, I don't need to kind of talk about what locally hidden variable models are, or why they're kind of interesting, but they go kind of back to a very fundamental question about nature, namely the question of what actually happens if we make a measurement. In particular, could it be that the outcome is already sort of defined, already specified by some local hidden variable description, and I just don't know it yet, but I kind of uncover it by making a measurement, or is there really something else going on? So I guess most of you know that kind of Bell has already observed that in fact there would be a way to test this under some assumptions, namely that when correlations between distant measurement outcomes are limited, if local hidden variable models would be true, but using quantum states we can violate this bound. So the first one relates to the kind of statement that we want to falsify, and the second one just gives us a means to kind of construct the experiment. I think it's important to understand though that kind of a Bell experiment says absolutely nothing about quantum mechanics. It does not say anything about entanglement, whether entanglement exists or not. But of course we kind of think that this is a description of what we have to do in the lab in order to come up with a violation of a Bell. So I suspect that most of you actually have seen this formulation of Bell inequalities, but it will be actually very convenient also for analyzing of gaining confidence in the Bell experiment. So let me briefly go through this. Okay. So I guess you know that Bell inequalities have been written as properties of expectation values, but people kind of like a modern perspective on Bell inequalities in terms of gains. In fact, any kind of Bell inequality can be described as some kind of game, and a very simple of these games corresponds to the CH-SH game that corresponds to the, as you may have guessed, the CH-SH inequality. So what does this game look like? So this game is played between two players, and we call it Alice and Bob. So Alice has a box, may contain some system, actually we don't know, might be described by local hidden variables or quantum states, I don't know. And on the other side there's Bob. And we kind of conduct this experiment by asking questions to Alice and Bob. So you can think that kind of Alice and Bob, in fact, play against us. So they want to win the game, and we want to see how well can they win the game. So the kind of questions that we will ask to Alice is that, okay, we will in fact just pick a bit. Okay, so this is the input, theta 0, 1. And we will also pick an input bit, a question to Bob, theta being 0, 1, and they produce some outcomes, which are also just bits. And we'll say that Alice and Bob win the game if and only if the kind of product of their questions is equal to the sum mod 2 of their answers. Okay, so what this simply means is that if both of them have a 1, then we want them to give different answers, and if either one of them has a 0, then we want them to give the same answer. These are the rules of the game. So when thinking about kind of Bell inequalities as a game, we like to think not about this kind of correlator, but in terms of the winning probability of the game. Actually, they are kind of the same thing. One can rewrite one into the other. It's very easy to see that. I can show you later. So what we're going to be interested in is the probability of winning the game averaged over the choice of questions. So these are the questions, so we average over them. We choose them each with equal probability. That's the ideal case. Here I'm kind of summing over the outcomes. And we're interested in, for a particular pair of questions, what is the probability that Alice produces answer X and Bob produces answer Y. So of course you are now asking yourself, how is this probability distribution generated? Like what probabilities are possible? So the first thing that you might observe is that, well, if we play this game while Alice and Bob can talk to each other and communicate, they can of course always win the game. Alice is simply going to tell Bob, look, I got a 0 or 1. Bob also sees, okay, I got a 0 and a 1, and they can always conspire to give the right answer. So the first thing is that kind of Alice and Bob should be separated, so they should not be able to communicate during the game, which means that certainly we would want that this distribution here is no sigma. Okay? So this puts a constraint on the set of allowed distributions. So it turns out that in fact, it's quite beautiful, I'm not going to talk about it here, that if this would be the only constraint, that no signaling is the only limitation, then in fact they could win this game with probability 1. This has been observed by Pesco and Röhlich. But quantum theory is strictly more limited. So if Alice and Bob employ a classical strategy, and what it means, classical strategy, what does it mean? You can think that a classical strategy is simply a function that takes the kind of input for Alice and produces a certain output X. You can also think about it as a lookup table, where basically it says, okay, like if I get input 0, I'm going to say 1. If I get input 1, I'm also going to say 1. Some structure. Of course, Alice and Bob might also, what in computer science we like to call shared randomness. So they, in advance, basically shared some randomness. They come up with a joint strategy, and depending on this, they apply certain functions. So using any such strategy, in fact, it's quite easy to convince yourself that the maximum meaning probability is 3/4. And it's kind of easy to see how this can be attained. Remember that in 3 out of the 4 cases, either one of them will have a 0 as an input, so they have to give the same answer. And of course, Alice and Bob can just agree to always say 0 all the time. They always give the same answer, and they will be correct in 3 out of the 4 instances. So it turns out that using a quantum strategy, and a quantum strategy means here that Alice and Bob can decide on to share a certain state, for example, an EPR pair, the maximally entangled state, and they can decide, depending on their measurements, inputs to perform certain measurements. For example, if Alice has input 0, they might say, aha, I'm going to measure sigma x. If I have input 1, I'm going to measure sigma z. Okay, so this is a quantum strategy, means that a choice of state and a choice of measurements that gives you this kind of probability distribution. So Tiersen has shown that in fact this is the best that quantum can do. So there exists a quantum strategy that can win this game with probability roughly 85, and this is also the best quantum can do. Okay, so quantum actually curiously is more restricted than no signaling, but better than classical. So the goal of a Bell experiment is, I guess in the first part of my talk, is to just find out, is nature classical, meaning it's described by these local hidden variable models that just give input-output behavior, or is there something else going on? Like I said, I think it's important to understand that the Bell experiment says absolutely nothing about why we observe a larger Bell violation. It just rejects kind of a classical description. So there's been many Bell experiments, of course, around, but all of them had certain loopholes. For example, I guess already some longer time ago, people have done loopholes, where, however, kind of they don't detect, always observe a detection event. And if you want to think about games, you can think that we will change the game where Alice and Bob cannot say just 0 and 1, but they can also say, I don't know. Or maybe if they would say, I don't know, I'm randomly generating either a 0 or 1. But in any case, this kind of lowers their probability of success. Or if I allow them don't know, they can kind of tweak in the direction that they want. For example, one strategy could be for Alice to say, well, if I get a 1, Bob might also have a 1, that's kind of bad, we would need to give an opposite answer. So in that case, I just say I don't. So this leads to the fair sampling loophole, which has been present in these experiments, even though they've closed the locality loophole, meaning that Alice and Bob are sufficiently far apart that we know that they cannot sneakily communicate during the game. There have been some other experiments which closed the other loophole, okay? Meaning that, yes, we don't have these don't know answer that require fair sampling, meaning they behave the same every time. But we are too close together. So it could be that there would be the possibility that Alice and Bob still communicate during the game, and therefore kind of trick us into believing that nature is not classical, but actually maybe it is. So these requirements, in fact, that we want here, namely efficient state detection, meaning the boxes always produce an output value in each trial, is somewhat difficult to reconcile with the fact that they are far apart. And you can think that in some kind of photonic experiment, of course, the fact that I may not see an outcome just simply happens because, like, if I send a photon somewhere, it will get lost on the way. And of course, the further I put them apart, the more likely it becomes that the photon is simply lost. So it's somehow very difficult to combine these two requirements together in one experiment. So fortunately, kind of Bell himself, in fact, already kind of proposed a solution to this, where he says, so let me actually add a box in the middle. Okay? So I'm putting here kind of the original scheme by Bell, where kind of because this, I used the original picture from Bell, kind of in this case inputs are here, outputs are there, so it's now from the bottom to the top, and we add this box in the middle which is called Go. And what this means in terms of a game, if you want to think about it this way, is that we basically add a third player, which I'll call the event ready station. We're not going to ask a question to that player, but it produces an output which I'll call T01. So 1 being for yes, let's count this round of the game, and 0 being let's forget about this round. So you can see that, of course, if these play Alice and Bob conspire against us, okay, you should always take this cryptographic perspective here. Also now the event ready station might conspire with Alice and Bob against us to convince us, in fact, that nature is not classical. Okay. And you can from that see that, of course, it's now important not only that Alice cannot talk to Bob, kind of before he produces his output, but also we don't want that if Alice has an inconvenient input, so to say, like say she has 0, 1, and she doesn't like that, that this is already communicated to this event ready station. So in particular, it should not be, for example, that there is enough time, so to say, for Alice's input to travel to the event ready station, for example, input being 1, and then the event ready station saying, oh, I don't like this game, let's ignore that one. Okay? So it's important now that kind of all of these are separated. So how this was implemented in the Delft experiment, like I said, it's not an experimental talk, and I actually don't want to talk too much about this, but if you're curious. So how this works in the Delft experiment is basically, here is Bob. I think that Bob is 1 diamond, Alice is also a diamond, and in this diamond there's an electron spin that is entangled with a photon. Okay? This photon kind of will be emitted and travels to this event ready station, which is going to do some kind of measurement, like a Bell measurement, essentially, that with some probability will say yes or no. Okay? Like go or not, like t equals 1 or t equals 0. So like I said, this is not an experimental talk, but maybe you want to see what it looks like. It's kind of nice. So like I said, in the Delft experiment, Alice and Bob kind of are, the qubits of Alice and Bob are stored in nitrogen vacancy centers in diamond. Actually, they're very nice. They have very nice properties. I guess we're not talking about this. And in particular, they allow us to have kind of very efficient readout, okay? Meaning that we can close the detection loophole. We can produce an outcome all the time. Okay, so Bob actually looks the same. I don't want to show you to Bob. So like I said, how is entanglement generated? From these diamonds, one can locally kind of create entanglement between an electron spin in the diamond. So you can think this is just a 2-level system, a qubit. And a photon will travel to this intermediate station where one basically does an interference, projecting the 2 photons, basically performing a Bell measurement, which creates entanglement between the electron spin in the Bob diamond and the Alice diamond. So you can think that what this does is really just entanglement swapping. If you want to think about it theoretically, so what this intermediate station does, it kind of does entanglement swapping, and it creates entanglement between Alice and Bob with some probability. Okay? And there's a tag, T, that says T equals 1, success, or T equals 0, failure. So kind of this efficient readout and the very efficient control in these diamonds kind of allows to close the detection loophole. And the locality loophole was closed by putting Alice and Bob sufficiently far apart. Okay, so this is Alice. Actually, this is where QTech is and where our offices are. This is Bob at roughly 1.3 kilometer distance in, I guess, a nuclear reactor facility on Delft campus. And here in the middle, C is in the engineering department, is this intermediate station. So like I already said, timing here is obviously of the essence. So let's actually first have a look at this picture. So here kind of we're ignoring kind of the intermediate station. So it's important, of course, that kind of the random number or the input basically, so this is the generation of the random input, the question that we're going to ask to Alice, does not have time to travel to Bob's side before he produces his output. Okay, so in this graph, like this here is basically when Alice is producing the output and when Bob is producing the output. Okay, like say in a moment a bit more about reducing outputs, which of course is a question. Okay. So of course it's important that A and B are space-like separated, but as I've already mentioned, it's also quite important that this intermediate station cannot be influenced by the input. Okay. So this means that kind of the generation of the random number, the generation of the input bit, like the question, must be space-like separated. In particular, this should not have enough time to travel to this intermediate station and say, let's ignore that round because I don't like my input. So I think, like I said, it's important to understand what can and cannot be tested in a Bell experiment. Okay? So like I said already, one should distinguish very carefully between the quantum description. The quantum description gives us a means to come up with an experimental design, but there's nothing quantum mechanical being tested here. But also, I've already said, the random numbers will generate the input, and we will record the output at a particular time. Okay? So of course, there's a question, can random numbers at all be generated? I don't know, maybe the universe has conspired since the beginning of time to thwart this particular experiment. That is certainly a possibility. There's also no way really to prove that measurement outcomes are final at a particular time. Okay? So actually in our experiment, in contrast to some others, we have taken this time actually to be quite conservative in the sense that we say the measurement outcomes kind of exist or have been produced when actually the measurement outcome is recorded on kind of an electronic device. Okay? Yes. So we've been quite conservative and careful here in defining this, but of course there's no kind of guarantee. Even if I were to observe this measurement outcome, you know, like there's no saying whether the measurement outcome has been produced. You know? So these are kind of assumptions that one has to make kind of in every Bell experiment, and there's no way to test these principles in this way together with the Bell experiment. Okay. So I should say that, like I said, the Bell experiment only kind of tries to refute local realist theorism that kind of say I have randomness to test, and that also say that the outcomes are final once they're recorded in the electronics. So there have been some further experiments, purely in optics, by Justina from Vienna, in the group of Zeilinger, and also Christer Schalm at NIST, which appeared like shortly after our work. Okay. Great. Very good. So I want to talk a little bit now on how we can actually draw any conclusions from such an experiment. Like I said, one should already kind of be a little bit careful about what conclusions can or cannot be drawn. But the question is, how can this be analyzed? And it turns out that this kind of describing this Bell experiment as a game actually makes it quite easy to do statistics and to see what we would have to compute. So of course I told you that kind of local hidden variable models imply these limits on these probabilities, but you know, probabilities is not something that one can ever observe. Okay? Like in an experiment one can only count stuff, like how many times does a certain event occur. And of course this experiment also does not run, I don't know, until the end of time, but of course it only runs for a finite number of events. Okay. So the question is then kind of, what does it mean? Kind of what actually is the statement of a Bell experiment? So a Bell experiment is essentially kind of a hypothesis test where the statement to be rejected, the hypothesis to be rejected, is the fact that the experiment is governed by a local hidden variable model. And kind of statistical confidence can then be, I guess, like in any hypothesis test, this is of course not something that we invent, defined by something called the p-value, which is the probability of observing data at least as extreme as the one observed. This, of course, is quite a mouthful, but note that if we think about this as a game, it is actually very easy to see what that means. So the question what we're interested in is, what is the probability that the local hidden variable model would have won the game at least as many times as the number of wins that we've recorded in the experiment? Okay. So from that perspective, it's very easy to analyze this, because basically we just play the game, we count how often do Alice and Bob win, and then we're interested in the the best kind of possible local hidden variable model, what is the probability that it would have won at least as many times? Okay, like there's a rigorous bound. In particular, there's no assumptions that the experiment is IID or that kind of the variables behave Gaussian, which is what you would get if you were to just give standard deviations away from a mean, basically, like from the correlator that one often gets. So Gil, I guess, is kind of one of the people who kind of pioneered the closure of what he called the memory loophole, which is actually not a fact of the experiment, but a property of the analysis, where one kind of allows the local hidden variable models not to have any memory. But of course here we want to close all the loopholes, or at least all the closable loopholes, so we do allow. So of course if you come from computer science and you think about these games, there's a classical strategy. What is the probability that we win so many times? The question now becomes quite easy. And all we have to do now is to first kind of write down what is the hypothesis that we want to test. So like I said, I'm being a bit informal here. The hypothesis that is tested is, okay, there's free will, like we can generate these setting choices independently from each other. The inputs have a bias, actually it's enough to constrain the average bias from uniform. Of course, again, you know, like one can test this random number generator. Ronald had a master student test this random number generator for like 10 months on all kinds of temperature conditions. There's a theoretical model of this random number generator, but you have to believe that random numbers can be produced. The second assumption, or I call it here an assumption, is, or part of the hypothesis, is what I call no signaling, meaning that kind of Alice cannot influence Bob and Bob cannot influence Alice. This is basically ensured by the experiment, at least if you believe in special relativity, the fact that they're too far apart, like namely too far that they would have had time, according to special relativity, to communicate to each other. Okay. So again, maybe you don't believe in special relativity. No, that's okay. And I make this here explicit, so our analysis, I would like to emphasize, actually also explicitly kind of takes this event-ready station into account. It is actually theoretically relatively clear that kind of giving power to the event-ready station does not change the behavior of this function, but of course we want to kind of make this form. So we can now kind of, for one round, and basically that's a derivation of the CHSH inequality with some extra terms that just come from the fact that the random numbers are not 50-50, but slightly kind of imperfect, derive on the probability that Alice and Bob win one round of the CHSH game, conditional on all the history and, of course, the rounding time. Yes?
Right, this no signaling conditioned on the history sounds a bit like IID. What's the kind of...
No, so we're not assuming here.
You're not
that
assuming IID, but what do you mean conditioned on the history, that there's no signaling even...
So I'm saying that kind of the no signaling fact is not affected by what came before in the experiment.
Okay, right.
Yeah. I guess if you believe in special relativity, then that is true. Yeah. Okay. So note that the only way I mention this is because, of course, we first derive something where all the probabilities are conditioned on the history. So then we... Right. Then there's kind of an easy calculation, but well, actually it's a little bit annoying, but otherwise... So we bound the p-value, so basically we say what is the probability that Alice and Bob win at least k times in n trials. Okay? So n is the number of what we call trials, and the trial is where the event-ready station said, yes, great, t equals 1. K is the number of wins that are recorded in the experiment. This here is the bias of the random number generator. So what is this n here? So note that, of course, if we allow full control of the event-ready station, kind of local hidden variable model may try to produce a certain number of wins using a much larger or smaller number of attempts to make entanglement, say where t might have been 0, than we actually observed in the experiment. Okay? So in particular, I don't know, so basically every time we attempt to make entanglement, it doesn't always work. T might be 0, but we allow, of course, a local hidden variable model that is kind of keen on producing a certain number of wins to have any strategy of this event-ready station. In particular, it might also use arbitrarily many number of attempts in order to kind of produce a certain number of wins. Okay? So basically stop after a certain number of trials is reached. And, but of course, if you compute the p-value the number of attempts might be much larger than what we've seen in the experiment. Okay, but this is actually not so difficult to bound using a recursive argument. I'll say that in a second. So how one does this? So in this experiment, which was done a year ago, roughly, there was one event per hour. Actually, currently this goes much faster, but of course we were keen to kind of, I guess, finish the experiment. So at this point, we had to be very patient because there was only one event, meaning one trial, one kind of, yes, we successfully made entanglement roughly every 50 minutes to an hour. Okay? So we've collected 245 events over 220 hours, which is a very long time. And we've recorded 196 wins. Okay? So how to interpret this? Well, like I said, this is a hypothesis test. We want to reject this null hypothesis. And there's a p-value, probability of observing at least 196 wins in 245 trials. The p-value in this experiment is roughly, it's just below 4%. So let me maybe say something about the magnitude also of the p-value, because I guess some people seem to be quite obsessed that in high energy physics, of course, p-values should be on the order of 10 to the minus 6. So note that here there's nothing like a look elsewhere effect, like in high energy physics, for example. The null hypothesis is completely specified, like this is the null hypothesis, and this is going to be tested. Okay? It's not like we don't know the mass of the Higgs, and therefore we're going to try and get a much smaller p-value, just to make sure that even look elsewhere effects are kind of covered. Because there's no look elsewhere effect. Yes.
But at the same time, you're trying to use it was kind of conspiratorial, right? So would that make sense to take people all going public?
Well, so note that what we have done here, okay, so in a statistical test, it is kind of important not to run until the p-value is small enough. In fact, this is a common, I guess, fallacy of applying this kind of analysis. Because note that, of course, the p-value can fluctuate. You can kind of be lucky for some time, okay? And then you might observe that you see a low p-value. So one should certainly not do any experiment where I just keep running until my p-value is small. This is statistically invalid test. Okay?
They have not put a paper on the arXiv, they said they removed the whole thing.
Excuse me?
But they have put an update on the arXiv that says, I can edit statistics.
Well, so I'm actually an author of both of these papers, so I can tell you what we say in this paper. So we do have put another paper on the arXiv, but not because our statistics were insufficient, but because people were asking, is your experiment stable? And in particular, I will say more about this in a second, there was a question of whether our random numbers are somehow correlated. So we wanted to do another run just to be clear. But we did not do another run, because we thought the p-value was too large. In fact, this is definitely not the case. In fact, after we finished this, Ronald immediately wanted to move on to only thinking about quantum repeaters from now on. Okay. So like I said, the proof idea, I guess, is quite simple. The only kind of more difficult part is that we need to kind of deal with a long string of attempts as opposed to the kind of short string of trials. But there's an easy inductive argument to do that. I would like to emphasize that actually we can kind of extend the analysis that we've done for this particular experiment to, in fact, large classes of Bell experiment. In particular, all games which are win and lose, we can actually derive a p-value which is tight, okay, in the sense that there also exists a strategy to achieve this kind of winning probability for the classical model. And the argument here is actually very similar, which is basically just count, win and lose, how often do they So all Bell experiments, like I said, can be mapped on a game, but not all Bell experiments will lead to a win and lose game. Okay? So you might have a Bell experiment, I guess also in like a normal game, where you don't just win and lose, but you get a score. For example, if you get some answers correct, you might win, I don't know, 2. If you get others correct, you might win only half. So in this case, kind of, I guess things become a little bit more complicated. But of course, once you think about it as a game, it is also quite clear, as was already observed by Gill, that this is obviously a martingale, and therefore one can just apply martingale concentration bounds to get a bound on the p-value. Okay? So we've used actually some very beautiful martingale inequality put forward by Benkus. I very much like this inequality, so I encourage you to find this out. Somehow it is not very well known, which is almost the same, basically, as for the win and lose game, apart from this factor. Great. Okay, so now let me kind of go back to your question. So given that there were some questions of is your experiment stable enough, or in particular, are your random numbers somehow correlated? It was decided to take more data. So actually this time Bus decided to take data, and he decided to run until we observed 300 points. So 300 trials, and we recorded a p-value of roughly 0.06. So note that, like I said, if you do the statistics, you do not run until the p-value gets low enough. You think in advance on some calibration data, how long do I roughly need to run in order to achieve a p-value that is less than 5%? Okay? So in this case, we observe a p-value of 0.06. Like I said, maybe the only thing I want to point out here, because some people said, oh, your random numbers are somehow biased, violate the no-signaling principle. There's no evidence for that on the data. But note that, of course, once you have taken data and you stare for it, at it, you can, of course, find all kinds of patterns in data. That, I mean, this is not statistics, right? This is just look elsewhere. In fact, I would just like to emphasize, and this is actually the motivation why we did the second run of the experiment, is that our random numbers, I guess, is not biased, and one can see it again here, and you can also compute kind of what is the probability that I would have observed any of these funny patterns, and that probability is actually quite large, which is not surprising. Okay, great. So basically, in all of these tests, we test an hypothesis. It's important that the hypothesis is formulated in advance and independently of the data. Of course, after I've seen the data, I can come up with all kinds of stuff that apparently kind of fits the data. It's important, like I said, the details of the test have to be specified in advance. One can do this also for other tests. For example, we've recently, I guess, our analysis has been used by Fedorov in some contextuality experimental tests, what we call an epsilon-bounded IIB non-contextual hidden variable model. It's a very complicated name, but it's just a formal definition of kind of the hypothesis that we're actually testing. And one can again just analyze this using this win-lose game. Great. Okay. So I'm very well in time. That's very good. So the first part of my talk, like I said, was more foundational. Kind of, I guess we used the Bell experiment to find something out about nature. In particular, we want to kind of reject that nature is classical. So I want to kind of up the game a little bit by looking at device independence. And the reason why I call this upping the game is that here our adversary is not even necessarily classical, he's even quantum, and nevertheless we want to kind of establish certain statements. So what is this device independence? You know, I am a theorist, so I really like the model of device independence, which works like this. I have a measurement device built by Ronald in the lab. I can give it some kind of input theta and will produce an output x, but I don't really know whether Ronald really put inside the box what he promised me. I don't know. So I want to be kind of secure, or kind of do quantum cryptography with this kind of mystery experimental apparatus, just by observing the input-output statistics. So we can give input. The device is otherwise arbitrary. Okay, it might have an arbitrary state, it might be hugely dimensional. Measurements inside, it might remember what kind of happened before. There is, however, kind of one small assumption, meaning that there's not a radio inside the box. It kind of transmits the outcome somewhere else. So it's basically input-output, and this is kind of the only input, the only output. Box might have memory, but only within itself. So there's a lot of history. I already had I'll give you some pointers in a moment, but you can also find a huge collection of references in this survey. So again, just to be clear, the kind of statement that we're testing here, the security does not hold. Yeah? So basically, from observing a Bell-Reiserer violation, we can reject the fact that we would be insecure. So I guess most of you kind of know quantum key distribution, and I guess one way to look at quantum key distribution put forward by Arthur Eckert is this very beautiful perspective that Alice and Bob try to make entanglement. Of course, we know that entanglement is monogamous, so if they were entangled, they know that nothing in the universe, in particular the eavesdropper, can have any correlations with them. And they can use a Bell test to test now when they're entangled. So basically how this kind of one way to look at these protocols is that kind of they try to make entanglement, they test some of these rounds, they check, do we win the CHSH game? Again, we can only count. And in the kind of live rounds, the ones that we didn't use for testing, so we would use key. So, I guess don't be talking about this, there's been a huge body of work on that. But I wanted to now talk about device independence that kind of goes beyond QKD, but applies to other protocols. So maybe I wanted to kind of just emphasize here that eavesdropper in QKD, of course, has quantum computer and quantum memory. He can prepare these devices and measurements ahead of time. He can learn all of the measurement settings, because like they will communicate, like which bases have we used kind of to test actually, they need to communicate with each other. But there's no quantum information essentially flowing back to the eavesdropper. Okay? This is analyzed as that this eavesdropper prepares these devices, and they might even kind of communicate with themselves quantumly in the middle, very funny models. But there's no quantum information. So one can, of course, do device independence for all kinds of protocols, and we have actually now devised various methods to do this for all kinds of protocols. But I wanted to apply it to a particular kind of situation, which is known as two-party crypto. Okay. So one of the problems that kind of Alice and Bob tried to solve in two-party crypto. So they wanted to solve the following problem. So Alice has an input x, known only to her, but not to Bob. Bob has an input y, known only to him, but not to Alice. And they want to compute some function f. Okay. And in the end, they want to, usually both, but maybe sometimes only one, learn the output of f of x and y. So of course you might say, well, this is very straightforward, you know, like Alice can just send her input x to Bob. So the kind of difficult thing is that there's no eavesdropper here. But unlike before, Alice and Bob don't trust each other. Okay? They had some kind of falling out after all of these years of doing QKD. And Alice wants to be sure that whatever Bob does is, yes, he might learn the output, f of x and y, but he should not learn more about her input x than he can infer from this output. Similarly, for some reason, Bob stopped trusting Alice, and he wants to be sure that similarly he cannot learn more about y than she could by looking at f. So of course, like we don't have these magic orange boxes that work like this, so they want to kind of build something that works like this ideal orange box by communicating back and forth over some communication channel. So let me give you an example of this, why we want to do something like that. So say Alice wants to sell a car. She might say this is worth 3,000 euros. Bob says, well, you know, I think this is worth 3,000 pounds. Of course, the question is whether you asked this question before or after Brexit. This might be one thing. And the function that they might want to compute, I don't know, might be the following. So the output should be no if kind of y is below, sorry, if x is below y. So kind of Bob wants to have y pounds. Alice bids x pounds, so if Alice doesn't match kind of Bob's asking price, then no go. If, however, kind of Alice kind of bids enough money, then in fact the output will just be x. Okay? So this kind of means that if Alice always thinks she gets a good deal. If they decide to sell the car, then she gets it at the price that she bid. She never learns more about Bob's input, except that it was lower than hers, so evidently she has a good deal. Okay? Bob also does not know kind of, if the answer, for example, is no, Bob does not know kind of what exactly was this x, so he also cannot tune his y to maybe sell his car better. Okay, so it's kind of a simple example of such a function. So there's other examples, actually, let me skip that one, where they want to compute the equality. So the kind of very difficult thing, or that makes these protocols in general more difficult than quantum key distribution, is really that Alice and Bob don't trust each other. So they cannot kind of check on the eavesdropper kind of by working together, but they're alone. Okay? In particular, like if Bob, for example, is dishonest And in device independence, you would say, if Bob was dishonest, he might have prepared the device of Alice. Then there's no way that kind of Alice can rely on the answers of Bob to do any kind of testing. That's another thing. So, how we will test these devices? Actually, that's not the only way, I'm sure, but there's one way that actually works for a lot of protocols. Is that we change the situation slightly by introducing more than two boxes. Okay, like in QKD we had an Alice box and a Bob box. Here we will have a few of them. In particular, we'll say, well, Alice has her normal box, and in addition, she has what I'll call a test box. Okay? And there's a source, and the source kind of can produce an arbitrary state, can also be prepared by Bob, and Alice can decide. So the source always sends one half of the state to the Alice box to be measured, and the other half can either go to the test box or kind of live to Bob in the protocol. So like I said, I've kind of put this here in red. Kind of an important difference between QKD is that also makes the analysis rather different, is that now there is kind of some kind of quantum or part of the entangled state being going really back to Bob some of the time. So if Bob is dishonest, he might have some arbitrary box here, which I call the attack box, that he might use to try and break the book. So there's all kinds of cryptographic primitives. I don't really have time to talk about them. I will just give you a very simple one. So certain primitives called bit or string commitments are shown to be impossible without assumptions. Okay? So in QKD there's no extra assumptions on Alice and Bob. But one of the kind of intuitive reasons why two-party crypto, even using kind of magic quantum communication, needs extra assumptions is the fact that really Alice and Bob don't trust each other. They cannot kind of, in QKD they gain an advantage by being two parties that can check on Eve. Here there's only one party, so you kind of need an extra assumption. Great. So there's all kinds of assumptions, in fact, that can give security. Of course, there's classical kind of computational assumptions, like for example, you assume that it's difficult to compute the factors of a large number. There's also some kind of physical assumptions. For example, Alice and Bob are further split into several agents and they cannot communicate during the course of the protocol. That kind of the channel that connects them has guaranteed noise. Or in fact that they have a limited amount of storage. Okay? Of course, storing classical bits is kind of very easy, so that's not a very realistic assumption. But it turns out that there's kind of very interesting quantum assumptions that also relate to the fact that we're going to assume that it's difficult for the attacker to store quantum information for a significant amount of time, or rather a lot of quantum information for a significant amount of time. And these physical assumptions have one kind of nice property as opposed to computational assumptions, in the sense that they only have to be valid for a very small amount of time during the course of the protocol. So in the protocol we'll have kind of a waiting time, and during this waiting time the attacker cannot store more than, I don't know, 1,000 qubits, for example. But if he buys a 2,000 qubit memory 5 minutes later, he cannot retroactively break the security of these protocols. So there's some protocols which can actually be very easily implemented. Security is in principle, of course, always possible. We just need to send more qubits if the storage is larger. And like I said, security cannot be broken retroactively. So let me explain actually this kind of storage model, just to be kind of clear what this works. So on the one hand, we allow that the adversary is all-powerful, unlimited amount of classical storage. His actions are instantaneous. He has a quantum computer, in fact, to encode and decode information in 0 time. And so the only limitation is that he cannot store an arbitrary amount of qubits. And we will exploit this by introducing a waiting time in the protocol. So at the beginning of this waiting time, adversary might have a huge bunch of quantum information. He might measure some of that arbitrarily, store classical information, but his quantum information storage is limited. Okay, so there's some noisy channel, or if you want to think, just a certain number of qubits if he rewaits a certain time. And again, like I said, he can do an arbitrary encoding and actually also decoding, so he has kind of a quantum computer. So I'm going to show you kind of a very simple kind of cryptographic task that we want to achieve. It will seem a little bit obscure. But you can think about this as kind of a universal gate of two-party crypto. So if we can kind of implement this gate or this kind of functionality, then using kind of further processing, we can in principle achieve any other two-party crypto task. call this week string erasure. So what is this? So you can think that here it's just a box where randomly Alice gets a string, x1 up to xn. Bob gets an index set I, and the elements of the string x corresponding to the entries in that subset. So for example, if the subsets are now 3 and 7, then Bob will get bits x3 and x7. So there's some security conditions. I'll be here rather informal. So if Bob is honest, but maybe Alice is cheating, then Alice should not learn about the index set. So Alice does not learn which of these bits are belong to Bob. And if Alice is honest, but Bob is trying to cheat, then Bob's information about the entire string is limited. Okay, so in fact, kind of we are happy if he learns a random subset, so every index is chosen with probability half to be in that set. But his probability of guessing the entire string is small. Okay? So the min entropy is just minus the log of the probability that given kind of the best possible procedure, given Bob's classical information and whatever quantum information he kept in his storage device, he manages to guess the string x. So basically this just means that the probability of guessing the entire string is exponentially small. So what do we know about it? Like I said, it can be transferred, converted into all kinds of other cryptographic primitives, and oblivious transfer in fact is universal, so it can solve any crypto transfer. So I'm not going to do that here, but I just want to point out that in fact security can always be achieved if we trust the devices, if we send a number of qubits n that is at least as large as the number of qubits in storage minus some small logarithmic fraction. Okay, so this is essentially optimal because the protocol will be insecure if we can store everything. In fact, one can prove there's no protocol that can be secure if the number of qubits storage is equal to n. So this is kind of close to optimal. So in this talk, to give you some intuition about how one can establish security here, and I only want to give you some intuition, I will make a very simplifying assumption. Namely, I will assume that Bob can only store classical information and no quantum information at all. Okay. So there are some kind of nice lemma that relate, in fact, his ability to store classical information to his ability to store quantum information, or in a storage channel F. So we can also say this about a bounded number of qubits, but this is not the optimal way to do this analysis. Okay? I will go this way because it's kind of nice to understand. So let me first explain to you this protocol for this week's string erasure. In fact, all the devices work perfectly. Okay? So what is the honest protocol? It's actually very simple. It's exactly the same as in QKD. We do this n times. In each time, Alice picks a random bit. She picks a random basis. For example, Hadamard in computational, and she sends to Bob the bit encoded in the basis. Bob also picks a random basis. He measures and records them. Now we wait some time delta t, and afterwards Alice sends to Bob the basis information theta1 to theta n. Bob can check. Did I measure in the same basis? Then he adds that index to the set. And you can see now that kind of if there's no noise, of course in this talk there will be not any noise, that basically the output here, I said Alice gets a random string, x1 up to xn. This is just a string he generates himself. The index set that Bob has is just the elements where he measured in the same basis. And of course, if there's no noise, then he has the elements. That's right. So you can already see that kind of if there would be no waiting time, no storage assumption being applied here, then there would be a very simple attack where Bob can get the entire string. He simply stores all the incoming qubits, waits until the basis information arrives, measures all of them in the right basis, and he knows everything. Okay. This is kind of a crucial step. That there's some kind of waiting time. When we call it waiting time, but conceptually the storage assumption is applied. I'd like to emphasize that there's no storage here needed to execute the protocol, only to break the protocol. That would be a convenient thing. Okay. So to think about device independence, it's nice to think about a purified protocol, and this again works just the same as in QKD, where instead of preparing these BB84 states, like encoded into two different bases, Alice simply prepares an EPR pair and then measures in one of these bases to prepare the state. Because you've seen all this before. So like I said, I've kind of emphasized here that kind of quantum information goes back to Bob. And the reason for that is that, of course, in crypto, of course we want to be secure, but we also want to be correct. Okay? So kind of the difficulties that arise here is to combine the fact that we want to be correct and with the fact that we want to be secure. Okay, so Alice certainly will not learn the index set, so there's no information flowing to Alice. Of course, one can make it a bit more formal. So the difficult part is really dishonest Bob. Okay, so in the device-independent case, dishonest Bob prepared the devices, A in the test box, and like if everything would be fine, then this would generate an EPR pair. In every single round, Alice would make BP84 measurements, and A and the test box would run a Bell test to kind of check, is my EPR pair okay? But of course, we don't know really what happens. So like I said in this talk, I want to make a simplifying assumption. I will assume that Bob in fact measures everything. He just produces a classical outcome, K. And I will, for this talk, also assume that he does that in every single round, sequentially, immediately, and doesn't actually store things. So in every round, he will immediately produce a classical output, K. So note that in this case, basically we can, without loss of generality, assume that the classical outcome K is 2 bits. So this is the answer that Bob would give if Alice later says, I'll use basis 0. And this is the kind of guess for the string X, for the outcome X, if Alice says, ha, I've used basis number 1. So we call this the post-measurement guessing game. So like I said, the idea of kind of using Bell tests to verify anything is to show that kind of a Bell violation is incompatible with some other behavior. And because we've kind of combined this, we can actually just combine these games, where we think of this as a new game involving just 2 parties, where with some probability we play CHSH, and with some probability we play this post-measurement guessing game. Okay. And one can then see that there's kind of a nice trade-off. In fact, one can easily analyze it sequentially between the probability of kind of winning the live game, the post-measurement game, with the probability of winning the CHSH game. Okay. So this kind of means that if CHSH works very well, then his probability of winning the post-measurement game is not very great. And if, for example, I don't know, his probability of winning the post-measurement game is 1, okay, he actually would succeed at this a lot, the probability of winning CHSH is just classical, so we will quickly see that using the test box. Like I said, this is of course not the most general analysis, but it gives you maybe some idea of how this protocol is. Okay. So we recently have a much more general result, which we put on the arXiv soon. We also allow, we don't have to do any of this kind of simplifying analysis with this classical. I'm done, essentially. I just want to make one more point, namely that, of course, we can use Bell inequalities to kind of try and falsify all kinds of other statements. For example, we could also ask ourselves a statement. I will plug in that gravitational decoherence is larger than some amount. So it turns out that one can also be shown that in certain situations, kind of combining these things in a smart way, they cannot be true in the same time. So this kind of gives us a means to kind of use device independence, not just, I guess, to test crypto, but actually to test nature. Because of course you can think that we, as being rather classical, or at least I'm feeling rather classical, are also kind of limited in what we can do when we want to learn things about nature. I can only kind of say, I kind of made this measurement, these parameters, I give some input, then nature does something, I don't know, and then in the end I'll observe some outcome. So kind of my way to interact with the world is actually also rather device independent. So the question that we kind of ask is whether we can kind of learn the coherence possibly caused by some massive object in a kind of device independent fashion. So this is actually also possible, so we can make such an estimate even if quantum mechanics would be false. Okay? So one can, in fact, the nice thing about Bell violations is that they don't even necessarily make statements about quantum mechanics, but they really just make statements about probability distributions that kind of arise, and whose existence is kind of incompatible with certain other facts about nature. So it would be very nice to kind of see more of this kind of things like this. Okay, so we've kind of tested nature, we've ruled out these little Hindenburg models. Of course, the question is, can we do device independent for other protocols? For example, multi-party protocols. But I think I've just tried to convince you that it would be very nice to see device independence be applied much more generally to properties about nature we want to learn. So this concludes, I guess, what we're up to right now. I guess if you're interested in these experimental efforts, is that we're quite interested in I guess, quantum internets recently, quantum repeaters, and this I want to conclude.
For a very great overview of recent work. Time for one or two very quick questions. Oh,
So I might have missed this. You said in the first round you were gathering, you had one event every hour. Have you brought that time down? Has that time come down yet?
In this new experiment, in the 300, so no. So the 300 points were actually also, I guess, because the 300 points were collected to convince people that everything is fine, using exactly the same setup as before. So there's no change. Yes, so actually, so I should say that this is not my achievement, of course, that Ronald has been working very hard on improving this hour. So there's actually several reasons why this took like an hour. And one of them has something to do with properties of I guess, the NV, or rather like whether a photon is kind of absorbed. Ronald is now working on some kind of optical cavities to actually absorb a photon rather than a photon. But one of the other reasons why this went so slowly is that the fiber that was used in this Bell experiment was tailored precisely to the emission frequency of the photon from this NV center, which is roughly 630 nanometers. So it's not telecom wavelength. And the losses on this very special fiber that was used for this Bell experiment were enormous. There's already 8 dB loss. So this basically means that most of the time the photon just gets lost before it even got to the stations. So now actually Ron has some kind of telecom conversion almost ready, so then it's good.
one last question, Alexander.
Yes.
So now that the LHVs have finally where we should be looking next, there's all kinds of things that still be happening, like greater causality or certain things. So what is your personal intuition or which of these things could be really happening?
So I should say that my feeling about superdeterminism is somewhat agnostic, because if nature would be superdetermined, I would also be determined already to worry about this or not to worry about this. So I'm not feeling very strongly about the fact that nature might be superdeterministic. So I'm using my possibly superdeterministic inspired brain to actually think that we might not be superdeterministic. But that's just a personal opinion. I mean, there's no way of knowing this, right? So.
Let's thank Stephanie again for